All right. So I said that kind of what we've been talking about is actually kind of important. It's a player in the formation of our solar system, which we're going to talk about in Chapter 6. Okay, and so this is kind of where that comes into play. Potential energy is stored energy. Potential energy is stored energy. Gravitational potential energy is stored energy because of gravity. So honestly, as I'm holding this up here, I have a picture to kind of go along with it. Okay, let's forget about my pen. As that this ball has been thrown up, okay, as it's here, before it starts to fall down, it has its most what we call gravitational potential energy. The reason we call this gravitational potential energy is it has the potential to let gravity kick in and it just goes. Okay. So when it's at the top of the arch, it has the most potential energy, gravitational potential energy, most PE. Okay. And then we said that as it falls, it's going to go faster and faster and faster. It's going to accelerate due to the force of gravity, 10 meters per second for each second it falls. So it's going to go faster and faster and faster. And remember that the faster something goes, it's going to increase its KE, or kinetic energy. Okay, so right here, right before it impacts, it has its most kinetic energy, and it has its least potential energy, because it doesn't have very far fall. Okay, so actually this kind of simple example is where potential energy over time is converted to kinetic energy. And then if you're like me, you're like, okay, so it splats, then what? Okay, so energy cannot be destroyed. That energy has to go somewhere. So I've read that basically a few things. One is if you hear a sound, that's part of the energy. Sometimes it'll heat up the thing it landed on, just ever so amount. Sometimes it'll bounce back up, okay? But that energy can be tracked. So kind of like that, kind of like gravitational potential energy, but not necessarily falling to the earth sort of thing. We're going to see that our solar system, that the sun and the planets, started out as something way big, okay, and it got smaller. So along those lines, if we have a gas cloud like that, our solar nebula, okay, as it gets smaller, it is kind of like that ball falling down towards the ground. It is actually having less and less potential, gravitational potential energy. Well, it needs to do something with that potential energy, and that potential energy is converted into kinetic energy. Okay, so this right here has a lot of potential energy, not much kinetic energy. Kinetic energy, again, that we can go back to the idea of having a thermometer reading that gas cloud. Okay, thermometer stuck in there. Those gas particles are not going very fast. Okay, so we make it smaller, less potential energy, but that has to go somewhere, and potential energy goes down, kinetic energy goes up. Okay. So when kinetic energy goes up, things heat up in the inside. So some of you already know that stars, including our sun, are great at, in their cores, they're like little powerhouses, nuclear powerhouses. Okay, so in the core of a star, in the core of our sun, it needs to be really, really, really hot and really, really, really dense. Those two things make it possible to go ahead and have nuclear fusion going on. So this heating up was important. Okay, it's critical. And it takes, well, let's see, hundreds of millions of years to do that. Okay, get smaller. As it gets smaller, it has less gravitational potential energy, but more kinetic energy. So we're going to see that again. So this is not a controlled nuclear reaction, but this is an uncontrolled nuclear reaction. Okay, so this is where actually a certain amount of matter, M, a certain amount of mass, M, okay, is converted to energy. So matter is converted to energy like that. And actually, you've probably heard of E is equal to mc squared. Okay, that was Einstein's equation to talk about how matter can be converted into energy. Way back with the Big Bang, when we start talking about that, a lot of energy was converted to matter, right? Tiny, tiny, tiny little seconds. Very small amount of time after the universe began. It was all energy. A lot of energy was converted to the matter that we know today, know and love today. Okay. Oh, and c in that is the speed of light, which is that 300,000 kilometers per second. Okay, so Newton's 3 laws of motion, Newton's law of gravitation. So that cool dance that we saw those galaxies doing with each other, okay, that's because actually in the center of most galaxies, including those, are supermassive black holes. That's not why they're dancing, but that doesn't help any, or it kind of adds to the gravitational pull that they have to each other. So the force that's felt between two objects, the force of gravity, this force right here, what mutual attraction is being shown here is the green one is drawn to the gold one, and the gold one is drawn to the green one. Mutual attraction. Okay? They each have a mass. We call that M1 and M2. So the pull that they feel towards each other is equal to their masses divided by their distances squared. This G right here is a constant. Okay? And again, you're not going to do any calculations. But intuitively, you probably figure if the more massive either one is, the bigger the force, right? The other thing is if you increase the distance, notice the distance is the divide by thing. So as you increase the distance, you probably think that the force decreases, and that's true according to that equation. So it's all kind of works. Okay, so note that the force of gravity increases with increasing mass, and it decreases with increasing distance. But this is why one of those masses, like if we're on the moon, we're 1/6 of the weight as we are on the Earth. But that's because the mass of the moon is so much less than the mass of the Earth. But that's also why, notice that distance there, black holes are so tiny, they're like so crazy massive, but they're very small. So basically the distance you are to their, you're like right there. So the distance is very small. As this becomes very small, look what that does to the force. That's what we got going on with black holes. Kind of getting ahead of ourselves. So this one kind of reminds me of the whole orbit thing, kind of the free-falling. If we were to take that same guy, which I don't think you could do this, right, Nellie? Take the same guy with the backpack, or, and he starts to orbit the Earth. Makes you want to go do it, though, doesn't it? And instead of kind of having just an insertion velocity, actually, if we had that person go ahead and go and I can't remember how fast it is, but a particular speed, he actually would escape the pull of gravity. Okay, that's called escape velocity. Minimum velocity needed to leave the gravitational influence of the object you're on. You break free. Okay, so the last subject is this. Okay, it's funny when I talk about tides, it's like here in Iowa, we're like, does the Mississippi River have tides? I don't think so. I have to think about it. I don't think Geode has tides. But a body of water that's large enough can give us tides because of the tug of the moon. Okay, so this is what this looks like. Basically, the moon, see if I have a picture here. Okay, the moon, we know the moon orbits the Earth, right? Wherever the moon is, basically the large bodies of water are kind of lifted up. Okay, if the moon tugs it. But as it tugs it this way, it actually also creates a few other things. It creates, so this would be high tide near the moon, high tide near the moon. It creates low tides here at right angles to where the moon is. and it creates another high tide on the back end. So we have two high tides created by the presence of one moon. Okay? So this is high, and this is high. Okay? And this is low and low. So what you're looking at is the North Pole. Okay, you're looking at the North Pole and the Earth is spinning. So do you buy this, that it takes 24 hours to spin once, right? So actually, here it's going to be 12 hours. So you have a high tide every 12 hours-ish. Okay? Anybody else lived on the coast? North Carolina? And you have a low tide 12 hours apart, but it goes, I guess it goes what? Every 6 hours you have something? High, low, ish. That's it. But there's a little bit of a catch, okay? So the sun also gives a tug. So when the Earth is smack dab in between, well, I shouldn't say that. When the sun and the moon are lined up, they can tug extra. So when I was here before, I kind of have my thing blocked. But if we make this yellow thing the sun, okay, and no, that's got to be, that can't be the sun. Let's make that the Earth, and the sun's over there. I think that's how we did it before. That's the Earth, and I'm the moon. Okay, so I'm the moon, that's the Earth, that's the sun. So what phase am I in?
High tide.
What's that?
High tide.
I am high tide. What lunar phase am I? You're right.
Full.
Full, exactly. I'm full, I'm high tide. Perfect. You got it. So this is where the sun and the moon are working together, okay? And also the sun and the moon work together here. What phase is this moon here? New, exactly. Yep, you got it. And those create what we call neap tides. I love that word neap. Spring tides. Neap tides. Sorry, spring tides. It's kind of like you spring up. Spring tides are created during full or new moons. Neap tides, sorry about that, are just the opposite. Basically, they are when the sun over there is at a right angle to the moon. Okay, so do you remember what phase this was? First and third quarters. This was third, and this was first. Yeah, so those create neap tides. Final answer. Okay? Well, actually, we're going to end there tonight. Dun, dun, dun. So we'll pick up with Chapter 5, which if you get a chance to read Chapter 5, that would be great. Chapter 5 seems a little technical, but if you at least just go through it, you'll be like, oh, I remember reading that. When I go over it next week.